Hello, my name is Tate Niekamp, and this is Lab 2 for Physics 2. Jumping into the introduction. So, the purpose of this lab is very similar to Lab 1, where we wanted to charge pieces of a Scotch tape and observe interactions with objects and other charged tape pieces. Then we wanted to determine the amount of excess charge on one piece of charged tape. However, in Lab 1, we treated these pieces of tape as point charges, where in Lab 2, we're treating the tapes as line charges. So that's the difference between these. Otherwise, the purpose is the same. So some physics principles that we're using is Newton's second law, F equals ma, or F equals mg with gravity. Newton's third law in electrostatic force, where two charged particles interact, creating an equal and opposite force. Coulomb's law, K q1 q2 over r squared. And the law of conservation of charge. So the main result, this came from Lab 1, was that the U-tapes repel. The tape was positively charged as it was attracted to a negatively charged pen. So if it was negatively charged, it would be repelled by the negatively charged pen. If it was neutral, the U-tapes wouldn't even repel each other. But since the U-tapes repelled each other, and the fact that the tapes were attracted to the negatively charged pen, we can conclude that the tapes are positive. And the tape's charge was 2.317 times 10 to the negative 8th, and I found that in this lab, treating it as a line charge. So the experiment, just to give you a little refresher. So we made two U-tapes and confirmed they were charged by bringing my hand close to them. The tapes are retracted to my hand. Then we determined the sign of the charge of the U-tapes by observing the interactions between the tapes and a charged plastic pen. That's what I discussed in the last slide. Then we placed the U-tape B, which is the system, on two textbooks as seen in the diagram below. Then we brought U-tape A close to U-tape B and observed the interaction while measuring the distance between the two tapes A and B. So tape B started floating. So tape B has the force of gravity mg pulling down on it, while the electrostatic force from A pushing up on it. So it'll float and the net force will be 0. So my predictions and actual observations. So I predicted that the two U-tapes would repel each other and that one U-tape would be attracted to a neutral object. And both of these observations or predictions were correct based off of my observations. So then assumptions and sources of error. So each U-tape, this is what we assumed. We assumed each U-tape had the same net charge evenly distributed along the length as we created them in the same way. And we also ignored air resistance. Some possible sources of error in this lab are largely based on human inaccuracies, like slight flaws when measuring distances or improper handling of the tape, causing a small transfer of charge. So lab 1 data, so my length of my U-tapes were about 21 centimeters. The distance between the U-tapes when they're floating was about 2 centimeters. And the mass of each U-tape was about 2.1 times 10 to the negative 4th kilograms. Conclusion. Jumping into my code. Skip verification. So here's my code for this lab. You can see the charge, estimated charge on the tape there. Going down. So then when you run this program, you can see that the magnitude of the electric force is the same as the magnitude of the gravitational force. The electric force is the white arrow. The magnitude of the gravitational force is the yellow arrow. So they're equal in magnitude but opposite in direction. Because the tape has net force 0 on it. So there's that 2.317 times 10 to the negative 8th charge. There are the two electric forces acting on the tape, the electric force and the gravitational force. And then the number of deficient electrons is basically the charge of the tape, 2.3 times 10 to the negative 8th, divided by the magnitude of an electron's charge. So we get it to be about 1.45 times 10 to the 11th deficient electrons on U-tape B. And then the number of atoms on U-tape on the U-tapes is about 4 times 10 to the 17th, which came from dividing the surface area of the tape by the surface area of an atom. Then we can find the ratio between these two numbers. So lab question. So what if I modeled each of my tapes as a single point charge like I did in lab 1? So the lab 1 charge, treating as a point charge, was about 9.6 times 10 to the negative 9th. While in lab 2, the charge as a line charge model is about 2.3 times 10 to the negative 8th coulombs. Both of these are in coulombs. So why do these estimates differ? Well, they differ because we're modeling the charges in two different ways. In lab 1, we assumed that the tape was a point charge with all the charges being in the center of the tape, while in this lab 2, we treated the tape as a line charge with all the charges being spread out in a line across the tape. So when we were trying to find the charges in the first lab, we set the force of gravity, mg, equal to kq squared over r squared, which is the electric field of a point charge. While in this lab, we set mg equal to kq squared over r times the square root of r squared plus L over 2 squared, which is the electric field, is the general electric field of a thin rod, and with the midpoint being on the axis. So that's what we did here, and that's why it's different. So the line charge model is definitely going to be more accurate, since a line of charges over the tape is closer to the actual distribution of charges on the tape, where the charges are spread out over an area.